Don Reicoski is, from Ohio and Ohio State, so it's always fun to have alumni around, right?
Good.
So thank you, Don.
Okay, well, thank you, Jay. First of all, I'm really honored to be here and would like to acknowledge the invite from Dave and Jay. And if this is too loud, can somebody wave a hand? Okay. So I'm honored to be here, and I've listened to several of the farmers talk, and I listened to Ray talk, and Ray used the word carbon several times. And yesterday, Gail Fuller used it 7 times in his speech that he gave yesterday. And I wanted to say hallelujah and amen for every time that he mentioned it. So my objective today is to help you understand what carbon means and why it's important that we manage it. It's nothing but a simple chemical element that is the major component of soil organic matter. So we talk about soil organic matter, and everybody understands that. And I'm not sure if I'm cutting out on that, but the soil, we call it soil organic matter because it's a mishmash of about 10,000 different chemical compounds. Out of those 10,000, the carbon is the key chemical in all of them. So I like to simplify things and talk about carbon. So don't be alarmed if you don't understand carbon, because that's my job today, is to help you understand that. So, my goal in life is to try to help maintain food security for future generations. And I have to compliment Gail again. He is thinking 4 or 5 or 6 years in his planning process. And I'm here to tell you that we in agriculture have to start thinking 5 and 10 generations, 400 or 500 years into the future if we're going to maintain food security. That's our responsibility. Right now, in 150 years of intensive agriculture in the U.S., we've done a lot of beat the heck out of the soil. And without that soil, we have nothing in terms of food production. 97% of our food comes from the land. There's some that comes from the salt water and the fresh water. So, carbon is very important, and I hope I can convince you that in this presentation. We have 9 billion people we anticipate in 2050 on about 2.56 billion acres of land that's around the world. We're being squeezed, and with finite resources, there's a good chance we're going to run out of room and resources to grow the food that we need. So we have some people that are hungry in this world. There's some environmental concerns about the planet. We're concerned about our children and our grandchildren's future. And I think one of our only chance is what we call conservation agriculture. And I'll tell you a little bit more about what that means. But part of that conservation agriculture is understanding that all of these things that we need rest on a living soil system. That living soil system depends on carbon, because carbon is the primary energy source for those little critters working for us in the soil. Just like you had this meal today, and I thank you very much for that, Dave, because that was a good piece of pork. You need 3 meals a day. These little critters in the soil need 3 meals a day, 365 days a year. Well, where I'm from in Minnesota, we have a little cool spot in December, January, and February that makes it a little difficult for much activity to take place. But we know about that, and we can sort of plan for it and help these little critters through some of those critical times. So my take on food security depends on this soil organic carbon. Without that, we don't have food security. We need soil quality that requires the physical, chemical, and biological aspects of it. We need environmental quality to take care of so we have a good place to live. And we have to be sustainable in doing this. And the total answer, my biases, is this organic carbon as the foundation for all of these needs of society. So this conservation agriculture requires minimum soil disturbance, continuous crop residue cover, and diverse crop rotations, and synergy crops or cover crops. This is what we're talking about. Some people take this and talk about a no-till system, but it's more than that. It's no-till plus some other form of carbon input. And all of these three keys of conservation agriculture are underlined by this soil organic carbon. Now the carbon comes into the system through this carbon cycle, through a process of photosynthesis. The carbon dioxide and the water vapor combine to make this sugar or carbohydrate, and that's how we capture the energy from the sun. The reverse of this process is called respiration, where we add a little oxygen to that sugar and it releases energy. And that's useful energy for us to do something. So you take this meal that we just had and you got some energy stored up so that you can go on and do your normal activities. Well, without the plants, we wouldn't be here. It's that simple. And I try to give you this idea about carbon cycling as a relatively simple process, but it's a very, very complex process, and the devil's in the details. So, as plant managers, you guys are carbon managers, and that's what I want you to understand in your responsibilities. I don't want you to look at that plant as trash. I don't want you to look at that residue, leftover material of little value. It's 46% carbon for this corn plant. So I want you to think about that when you see that plant. Even the green ones that you see out there, they're about 45, 46% carbon. So the plant has a tremendous amount of power in terms of capturing carbon, storing some energy, and it's a food source for us. When we take that grain and eat it, we have the energy that comes into our system. Same way with producing food for animal food. So the plant is very important to us. And through that plant, we are enabling carbon to get down into the soil through the root system. Those of you who heard Ray this morning about the importance of the root system, he's spot on. The root system is very important in terms of getting carbon into the soil, extracting some nutrients so that we can utilize it in nutrient cycling, as well as extracting water from deeper in the profile than we typically think about. Along with this, considering the plant as carbon, are many environmental benefits and a quality of life that I think is important to all of us. So when you look at that plant, think carbon. Now for you NRCS types, if I was teaching a class, you would memorize this phrase forward, backward, inside out. Carbon is the C, the chemical symbol for carbon, that starts conservation. It's not filling in the gullies. It involves stopping erosion. But if you look at the contour strips there, the corn plants there are 45 and 46% carbon. If you look at that grass waterway, that grass is about 45 and 46% carbon. You look at the no-till with a little bit of crop biomass on the surface, that's 45, 46% carbon. So what does that residue do? It does a lot of things in terms of absorbing raindrop impact, retaining and reducing water flow across it to minimize erosion, and on and on and on with a long list of conservation benefits. And so from my perspective as a soil scientist, and it's tough for me to admit that, conservation is more about plant management than it is about soil management because of the importance of carbon. And for a soil scientist to say that, well, I'm a half a plant scientist too, so I'm in the middle there somewhere. So, the farmer, you have these resources, the sun, the water, the air, and the soil. And your challenge is to manage these so we can optimize the ecosystem services from that landscape that you're working with. Those services are producing food, feed for animals, fiber, and now biofuel. And the heart of all of these ecosystem services spins off of the carbon cycle. I hope you understand the importance of that because I like to eat 3 meals a day, and so I'm going to make sure that I can maintain that. But I'm also concerned about food security for future generations so that we don't have to worry about our civilization crashing somewhere down the road because of poor soil management. So, intensive tillage does a lot to disrupt our natural systems. In agriculture, our responsibility is managing the water, the carbon, and the nitrogen cycles primarily. And if we do an intensive tillage event like the plowing, it disrupts all of these cycles because they are intimately intertwined and integrated into the overall process. And so any type of a tillage operation will disrupt all of these cycles. I'm going to tell you my bias about the carbon cycle because that's what most people are interested in and what my favorite topic. So, but I want you to understand that if I do something to mess up the carbon cycle, it's going to affect the nitrogen cycle and the water cycle. And it might affect them differently, but the three main cycles we must understand in agriculture, we don't want to mess any of them. We want them things to go as efficiently as possible so that we can optimize food production and maintain a sustainable production system. So, carbon is our greatest water management tool. And I'm going to say it again for Ray. Carbon is our greatest water management tool. Now, I'm going to extend the definition of carbon a little bit to include live plants, leaves and stems, dead plants, leaves and stems, the roots, biomass, some of the crop residue on the surface, the mulch layer, the particulate organic matter fraction, soil organic matter, aspects of manure, all the way out to humic acids. And so, carbon can increase the infiltration, increases the transpiration, it increases the soil tilth, the structure, the available water holding capacity, the water storage, the root depth, biological activity, and on with that long list that you can read faster than I can talk. The presence of carbon also decreases soil runoff and erosion, decreases evaporation and sediment loss, and also can do something to decrease the soil temperature, crusting, reduce pollution compaction, and desertification. What are the other things that we got to figure out how to manage in our agricultural production systems? So I want you to think about the role of carbon in all of these processes that we in agriculture have to contend with. An example of this water loss is illustrated with some data from University of Nebraska. They were comparing residue-covered soil versus non-residue-covered soil with irrigation. And what they were able to find that for 2 years of data collection, it was between 2.4 and 3.9 inches of extra water that was not lost due to evaporation when they had crop residue on the surface. Now, in a dry year, like you had here, was it 2012? 2 or 3 inches of water would have been pretty handy at that time. And so by keeping this residue on the soil surface, one aspect of it is a major water conservation which enhances the water use efficiency. It's not my data, it's their data, but that's the way they interpret it, and I think it's an excellent example of what this carbon management can do for us. So now back to one of my favorites in terms of understanding what we're doing to the system with intensive tillage. I want to talk to you a little bit about tillage-induced carbon loss from the system. If you look at the cloud of dust there behind the tillage implement, you can see that dust, you can feel that dust, you can taste it, and perceive that there's a problem. But with this carbon dioxide, 5,000 parts per million coming out of my mouth now, you can't see it, you can't feel it, you can't touch it, you can't perceive that there's anything happening. And so what I'm going to do is try to convince you with some data that there's a large burp of carbon dioxide that goes out of the soil when we do it intensive tillage. The flickering flames there represents a slow oxidation of the carbon to carbon dioxide. It's a slow burning process. And so when you do a major tillage operation, the oxygen concentration down in the soil may be 15 to 16%. And when we invert that with the plowing operation, it's exposed to 21% oxygen. And that's like pouring a can of gasoline on a fire. You got this big change in oxygen, the bugs kick into gear, and poof, out goes carbon dioxide. So we worked on developing this portable chamber technique to try to capture carbon dioxide and water vapor following tillage. It's nothing more than a clear plastic box mounted on the front of the forklift. And we take a sample of the gas back to the tractor where it goes through an infrared gas analyzer, measuring once a second for 60 seconds both the concentration of water vapor and carbon dioxide. That allows us to calculate the rate of flow from the soil. At the end of that period, it beeps at the operator, backs out and goes to the next block to make the measurements. So I told you that carbon dioxide was invisible, but I used those plumes from our ethanol plant to try to give you some impression of the gas exchange process that we are trying to characterize. That gas is invisible to us, so it's difficult to see that there's any kind of a problem. So this is the technique we use, and we gave it the acronym Mr. CHEM for Mobile Research Gas Exchange Machine. So we set up a study to try to characterize what was happening with several different types of tillage. And we used a no-till system where we ran the tractor through the plots to get the same amount of compaction as we would on our other treatments. Then we had a shallow strip till of the order of 2 to 3 inches with a fluted culture. Then we had a fertilizer knife that gave us a V-shaped zone of soil disturbance. Then we had another fertilizer knife that gave us a U-shaped volume of soil disturbance, a little bit larger than the other fertilizer knife. Then we had a low disturbance subsoil shank that went down to about 16, 17 inches, and you see the volume of soil disturbance characterized there. Then we compared that with the moldboard plow, which was down to 10 inches deep. So we made the measurements with that same chamber that I showed you before, and we made measurements for the first 8 hours after tillage, and then also at 24 hours and chased someone for 10 days after tillage. We take a look at some of the results with the cumulative carbon dioxide loss on the y-axis, and on the x-axis we have the different types of tillage. And on the extreme left, at 5 hours after tillage, we have the moldboard plow, the subsoil shank, the mold knife, the fertilizer knife, we call it residue manager, and no-till. And you can see at 5 hours after tillage and 24 hours after tillage, the decline in the carbon loss, with maximum the moldboard plow, and the minimum with the no-till treatment. And we've repeated this many times, and there's no question about what is happening. So we took that cross-sectional area that I showed you on those sketches that we measured, and if we calculate a unit length down the row, we can get a volume of soil disturbed. And that's what we have here. On the y-axis, we have the cumulative carbon dioxide loss versus the cross-sectional area. Yeah, but I got fat fingers. Just the red button. I'm colorblind. Maybe I can see that. Anyway, what you see is a fairly strong linear relationship showing that the carbon dioxide loss was proportional to the volume of soil disturbed in the tillage operation. So for those of you who have used a moldboard plow 10 inches deep, you also understand that there's a little more diesel required to pull that plow than some of those other forms of strip tillage, and a little bit more than with the no-till system. So we took a look at that, and my colleague Dave Archer has some information to show it in terms of fuel use. And so any type of intensive tillage becomes a double negative. The burp of carbon dioxide that goes out is proportional to the volume of soil disturbed in the tillage operation. The diesel required to do that soil mixing and tillage is also proportional to the volume of soil disturbed. This becomes a double negative with respect to putting CO2 into the atmosphere, affecting climate change. So intensive tillage becomes a double negative. And I think you can understand that the diesel required is proportional to the volume of soil that's disturbed, and that the CO2 goes out is proportional to the volume of soil disturbed. We did another study where we wanted to use the same tillage implement, which is a moldboard plow, and repeated it so that we had the same tillage implement with different volumes of soil disturbed. 4 inches is as shallow as we could go and call it inversion tillage, and 11 inches was as deep as we could go and pull it with the equipment that we had. And so when we made the measurements of that same chamber and looked at the cumulative loss for a 24-hour period, and as you can see with the no-till, we have a small amount that goes out, and at 4 inches of plowing, we get about 48 units. And as we go progressively deeper into the soil, we get this increase in carbon dioxide loss from the system. And so this is gratifying to me as a scientist because it's an independent test that shows, again, CO2 loss appears to be related to the volume of soil disturbed, whether you use the same tillage implement or whether you use different tillage implements. So what we're doing with intensive tillage does a lot to mess up the soil carbon. We had an opportunity to compare no-till drills. No-till drills are supposed to have minimum soil disturbance and with no pre-tillage condition. And so we asked the question, is there a significant amount of CO2 loss following these no-till drills? So we compared the green one, I don't have to tell you which one that is, double disc opener, and we identified that as a low disturbance drill, compared with the high disturbance drill that had a time opener. And so you can see some of the difference with respect to the way the soil surface looked after that planter went across the field. To give you a better idea what it looks like, we'll look at it from the field perspective. The non-disturbed area is on the extreme left. There's one pass with the low disturbance drill, pass with a high disturbance drill, a disc harrow, and moldboard plow for comparison. So I'm going to show you data for the 2 drills that we measured immediately after going across the field. And so on the left-hand axis is carbon dioxide loss, on the right-hand axis is water evaporation. So where we did nothing, there was a little bit of CO2 and water vapor loss. Where we did the low disturbance, we got this same CO2 loss and a little more water vapor. But with the high disturbance drill, I can't see it. Anyway, you can see that the 2 bars on the right side are significantly longer and taller than the low disturbance drill. And again, as a scientist, this is gratifying because even at these very low disturbance volumes, we're able to measure small differences that are significant, again, reinforcing the idea that carbon loss to the soil is proportional to the volume of soil disturbed. And it works at large volumes and it works at low volumes. Okay, I'm going to change gears a little bit and talk about soil biology. That's not my belly button, but I got your attention. You ask what's in your soil. The soil is a jungle full of different types of life. And this is a challenge to us when we try to understand all these little critters that are down there working for us. There's these bacteria and the fungi and arthropods and nematodes and worms and animals. And all of these are part of a biological system. Each of them little individual characters or microbes or soil fun are a system in itself, just like we as humans are an individual system, and we're different from each other because of some slight difference. So, there's a lot of tiny organisms that you don't see in the soil, but you have to understand a little bit about what they're doing if you're going to manage that system for optimal productivity. This is an example of some of them, and the sum total of them can be as much as 5% of the organic matter in the soil that we're working with. And I don't know what all those little critters do, but my favorite one is the night crawler because I like to go fishing for walleye. But they're all part of this team that's working for us in the soil. So if you're coaching a football team or a basketball team, you got to know how your players can work and contribute to the overall effort. Well, this is a difficult task when you have so many in such a complex system. But if you just understand that we're working with a living system, that's going to change your mentality so you start thinking a little bit different. So this living biological system that includes all the mammals, the moles and the mice, the worms, insects, the microfauna, mycetes, bacteria, and algae, if you summed all of them up, they require enough food to be able to feed 2 African elephants per acre of land. So that soil fauna and the microbial action that is taking place is equivalent to grazing these 2 elephants on an acre of land. If you understand that each of those elephants will eat about 300 pounds of hay a day, it takes a lot of energy, it takes a lot of carbon to keep them going. And it's the same way with the little critters in the soil. So, if we're going to plow, let's let Mother Nature do it. The night crawlers are one of the best ones in terms of making these pores, these biopores, for future root penetration, water infiltration. It's lining those things with mucigel and nutrients that are very important to some of them. And so from a physical and a chemical standpoint, the earthworm is one of the things that really helps us out in terms of managing the water, enabling the roots to penetrate deeper to absorb more nutrients, and other aspects of it. So this is something that we can see. But I want you to understand that the microbes that are there, which you cannot see without a microscope, are just as important. And when you look at the number of microbes per piece of the soil, it far outnumbers the earthworms that are there. So they each have a function, they're all important, and that's what makes our system fairly complex. But what I want you to understand is that with intensive tillage, I think it butchers the soil biology. The tillage implement cuts and slices and dices the soil, it blends and mixes and inverts the soil, and it creates havoc for the soil biology. As I showed you with CO2, if you don't till it, there's a small amount of carbon dioxide goes out. After a primary tillage, we get a major burst of CO2, and then with secondary tillage, we get a little bit less, partly because the soil is reconsolidated. And so, if we understand we have a living system, why are we trying to mess them up in terms of their activity and decreasing their effectiveness forms? From my perspective, tillage is a biotic disturbance, and I like to use the term turmoil of tillage. If the soil is a natural living system that contains a lot of life and is tilled intensively, it is dramatically changed. It can be considered analogous to a human reaction to a combination of an earthquake, a forest fire, a hurricane, an asteroid impact, a tsunami, and a tornado, all rolled into one perturbation event. Now, if that happened to you in your home 2 or 3 times, 4 times a year, you wouldn't be very happy, you wouldn't be very productive, you wouldn't be very efficient. And so it is with a lot of those little critters in the soil. We have to start learning to treat them with a little tender loving care if we want them to help cycle these nutrients that are important to us for our agronomic crops. There's a living system, and we have to treat it as that if we're going to be able to manage it accordingly. And the key component is feeding that population in the soil the carbon that's the most important part of it. So, intensive tillage opens up this all-you-can-eat buffet for the birds and the microbes. I don't know whether you guys got seagulls this far from Lake Erie or not, but the seagulls find the guys that are doing the tillage. And 20 to 30 minutes after the guy does the first pass on the field, there's a flock of seagulls following him. And I had one person ask me, do the seagulls smell the CO2 and find that? I don't know. But what I do know is that when you understand what those seagulls are doing, The worms that are sliced and diced, they're very easy for the seagulls to pick up. And so I think that we have to understand what we're doing to the soil biology with an intensive tillage operation. There's something going on there that's not good for the worms, because you can find pieces of the worms if you walk along behind the equipment. But tillage also contributes to other problems in terms of the soil degradation, and it contributes to laying the soil out bare for soil erosion. So now I'm going to do another little shift and try to explain what soil organic matter can do in terms of water holding capacity. Now if you take a look at this carbon or this organic matter and think of it as a sponge. You all know how a sponge operates. You dip it into water and you bring it out and it holds the water, but then if you squeeze it, the water runs out. Well, that's exactly how the carbon holds this water available for the plants. And so any soil that's high in this carbon and this spongy organic matter, it also releases some nutrients to the plant, but it can hold more than its own weight in water. And in drought years, that's pretty important. So we talk about available water holding capacity, some outflow, but that's what it is. It's plant available water. And it's a combination of the textural water, primarily from sand, silt, and clay particles, and then this spongy soil organic matter sponge water. And that is a significant portion of the water holding capacity. One of our NRCS colleagues, Herman Hudson, provides the data where he looks at available water holding capacity on the y-axis versus organic matter content by weight. And so you can see that for a sandy soil, it starts off at a lower value, but there's a slight increase as you increase the amount of organic matter. The silty clay loam and the silt loam, showing the greatest amount of water taken in and retained for the plants. So if we take a look at that and try to break that down and consider the water holding capacity as a bucket. If you have a small bucket, you have a small amount of water available. If you have a large bucket, you have a larger amount of water that's available for the plant when it needs it. So taking this example, with no organic matter, it would hold about 48/100ths of an inch of water in a foot of soil, foot depth of soil. But if you add 1% organic matter, that increases to 0.72, 2% organic matter, 0.96, and you can see what it is for 3%. Now this is a sandy soil. This is one of the most difficult ones to try to increase the water holding capacity. If we take a look at the silt loam soil, with no organic matter, it holds about 1.1 inch of water in a foot of soil. Adding 1% organic matter goes up to 1.5, and if you're able to get it up to 3%, it could be 2.54 inches of water that are held by that soil organic matter. This is a management tool for water. If you want to increase your water holding capacity, increase your water storage, there's a couple things you can do. Allow those worms to allow more infiltration, keep some residue on the surface so it doesn't run off, and once it gets into the soil, it's held there against the forces of gravity for when the plants need it and they can draw it from that reservoir. So soil and carbon, soil organic matter, is again one of our most important water management tools. One of the things about taking gears a little bit, the term conservation tillage. And my friend Randall Reeder, he's probably hiding so that he will cringe. Oh, maybe he's hardened to it now. He doesn't like my take on conservation tillage. One of the things that we need to understand is that the term conservation tillage, to me, is a little bit of a misnomer. But when you look at conventional tillage, defined as you see there, and conservation tillage defined as chisel plow tillage, and then no tillage is direct seeding. If you look at the runoff rate from those plots, this is not my data, this is some folks from the University of Kentucky. But if you look at sediment loss, the units are 15.5 for conventional, 3.3 for the conservation till, and 0.3 for a no-till system. Now if you take and put those on a relative basis, assuming that no-till is 1, then conservation tillage becomes 11. There's 11 times more erosion from conservation tillage than there is from the no-till system in this data set. Conventional till system is 52 times more sediment loss than with the no-till system. Well, unfortunately, the conservation tillage system is that T-value that the NRCS folks talk about, and I shiver from it, because it's larger than that 5 tons per acre that they say is acceptable erosion rates. Erosion rate should be 0. Because when we talk about building 1 inch of soil requiring 1,000 years, at that erosion rate, we're losing it faster than Mother Nature can make it. Mother Nature operates fairly slowly in regenerating this resource. And if we beat the heck out of it, run it down the hill, down the river to the Gulf of Mexico, it's going to be tough to get that back to do some good with it. So I think soil erosion should be absolutely 0. And I'm pleased to say that in the last 5 years or so, NRCS has gone away from the concept of tolerable erosion rates of 5 tons per acre. And you can tell your boss, Ray, that Reicoski said so. That's what I like. Okay. Some of these environmental problems are easy to see. And sometimes the water quality problems are not easy to see. But the example we were talking about earlier this morning about phosphorus and algae in Lake Erie, and it just kind of makes you cringe to see that. More importantly, that our guys in Minnesota get blamed for that nitrate that Ray was talking about, that slipped beyond the root zone, hit the Mississippi River and hit the Gulf of Mexico. Primarily because they're putting on more nitrogen than they need. And those things that you really can't see. Now you can see a little bit of sediment in the water, and so that's visible. But when you're preparing the soil, it takes an intensive rainfall event, just like the one that you had here a couple days ago, to result in erosion that becomes very visible. And once it's visible, it's easy to understand what's going on. So I want to make the point that poor conservation tillage, if you will, has consequences. With conventional tillage, the soil is completely unprotected, and you get what you expect when you get one of those intense rainfall. And now, conservation tillage, defined as non-inversion, leaving 30% residue cover, also leaves the soil poorly protected so that you do get some erosion. And only with no-till is the soil completely protected, and you get a very, very, very small amount of erosion. And so this term conservation tillage is a broad term used to define any tillage system with the primary objective of reducing soil and water loss. That's a very noble objective. And I think it needs to be continued. But again, the devil is in the details. We have to understand what is happening to that system, because with conservation tillage, with 30% residue cover, we have 70% of the soil that's bare and exposed to all the elements. What happens when you get 3 or 4 or 5 inches of rainfall in a 24-hour period? I don't have to tell you, you probably have observed it. So conservation tillage has very loose limits on the definition of soil disturbance and residue incorporation. And I think it fuels a misguided sense of entitlement and a misguided sense of conservation that's really not there. So, from my perspective, conservation tillage is an oxymoron. I think you all understand what an oxymoron is. And any form of intensive tillage is not conservation in the way that tillage degrades, fractures, and disrupts the natural soil structure. It disturbs the ecosystems and all the fauna that I can talk to you about. And these microbes are important in nutrient cycling. Tillage moves the soil down the slope by a tillage erosion. And it also loosens the soil, buries the crop residue, allowing the soil to dry and setting the system up for a severe erosion with the next high-intensity rainfall event. This is not my idea of conservation tillage. my perspective, most conservation tillage is more tillage than conservation. Conservation tillage is oversold for its conservation benefits. I think the concept is good, but the actual practice is not so good. That's because we cannot allow any soil erosion to take place. If we do, down the road, maybe not in your generation, not in the next generation, but 2 or 3 or 4 or 5 generations down the road, we're going to hit the brick wall, and there will be people suffering because of lack of food as a result of degraded land resources. So I want to move away from this term tillage, conservation tillage, and I want to talk more about conservation management. I want to emphasize conservation aspects, and I want to de-emphasize tillage. I want to emphasize crop residue management and de-emphasize the soil disturbance. And both of these point to carbon management. And so from my perspective, I want conservation without compromise. I want conservation without compromise. And to me, that means carbon management. My idea of conservation is by this song for this young lady, Shirley Murray, in 1992. I want to touch the earth lightly, use the earth gently, nourish the life of all the world in our care. If we had that attitude about the soil, we'd be a lot further down the road. So the action, or the conservation, by definition, is the preservation, the protection, and the restoration of the natural environment, ecosystems, and the vegetation. From my perspective, conservation is a word to be respected and revered. And it should be, and it must be used to describe agriculture. However, conservation does not belong in the same sentence with tillage. Why do we make this point? If you remember what I told you about the carbon loss being proportional to the volume the soil was disturbed, we have the extremes here on the left, looking at the volume of soil disturbed, the moldboard plow and the disc plow, they disturb a large volume of soil. We can go over here to our no-till system, which is a very, very small amount of soil disturbance. But between that no-till and this deep disc, all of those types of tillage are called conservation tillage because they don't invert the soil, they don't bury all of the residue. But I'm trying to make the point that the volume of soil disturbed, even though it's conservation tillage, can be awful large. And so this has led to a lot of confusion in the scientific literature, and it has resulted in a lot of opportunities for the equipment salesman to convince you that you're doing the right thing because it's a conservation tillage tool. And I've got Randall thinking about this, and as an engineer, he helps design some of that equipment, but I think he's getting a little better feel for why I think it's important, and when he smiles at me, I know it's okay. So to try to make that point a little more simply, with the conventional tillage system, we have zero conservation and much tillage. If we take a conservation tillage system, we have some conservation because there's some residue in the soil, but we also have some tillage. And with direct seeding, we have a lot of conservation and zero tillage. This is the best way we can do to manage the carbon so that we can maintain a sustainable production system. And Gail said something about farming in nature's way. All I can do is say amen to that, and I don't need to belittle the point because as we go from conventional tillage through conservation tillage to no-till, that's the closest way we can get to doing it in nature's way. We wouldn't disturb the soil the minimum amount we need to get that soil in there, get a little fertilizer in there, so that we can optimize the system. So Gail said it better than I could, and all I'm doing is trying to reinforce it. So, from my perspective, true conservation starts with this carbon that the C that starts conservation. And true conservation is all about carbon management. So there are two primary factors that can help us from, in terms of implementing the amount of conservation that's applied. No-till minimizes carbon loss. Synergy crops or cover crop mixes maximizes the carbon input. And I hope you understand that part of it. So when we're talking about conservation agriculture, we understand that we have a minimum soil disturbance, continuous crop resident cover, and diverse rotation and our cover crops. This is what conservation agriculture is all about, and I want you to understand the fundamental foundation of this is that carbon that we are trying to manage. It's very important to keep that because it impacts all of these things that are important to us in maintaining our agricultural production system. So, the other point that came out of what we were talking about this morning is biodiversity. And some of this comes in as cover crop cocktails. And I put all those C's in quotes because I want you to understand what that's doing in terms of carbon. Carbon, carbon, carbon. Cover crop cocktails. And I need to thank some farmer in North Dakota that came up with this word. It's been used, and now we have cover crop mixes and 10-way mixes and all of that. But what this is doing in terms of synergy crops is bringing together the individual benefits of each of these crops whose synergistic effects on the subsequent crops are greater than the sum of the individual crop contribution. To me, in my simple mind, it's adding 1 plus 1 and getting 3 as an impact. And that's what this is doing. And when you have 10 or 12 species in that mix, you just multiply that out in your mind and you'll get an idea of the impact that's, I think, is important to us. So we're fortunate to be hosted here by the Radish King. And Ray gave you an excellent example of what that tillage radish can do. And well, I think Ray is probably the father of the tillage radish in the U.S. I think that David was one of the first ones that utilized it in a field situation. And I'm a fisherman. I like to brag about big fish. He's a no-till farmer, and he likes to brag about big radishes. But I hope you understood what Ray said about the importance of radish and what it can do. I'm not going to repeat what he said because he said it in a very good way. What I don't understand are these mixes. And I think this slide was shown earlier, and the only thing I can say is that David tries to play scientist, and he swags putting these different combinations together. And I'll tell you what swag means after the presentation if you're interested. So, one of the tricks that David learned very quickly is that we got to control that cover crop. We got to manage it. And you see all the implements out here in the yard and the way he has come up with it. Now I'm sure he'll tell you that it wasn't a gravy train. There were some lessons learned, some mistakes made, but after a few years he's making it work. Okay? So, this carbon that we're looking at tries to protect the soil. We can have live crop biomass with an active protective blanket. We can have dead crop biomass with a passive protective blanket. And both of these are good for various types of reasons. So, Ray was trying to make the point that cover crops are more than for erosion control. They are multitasking. They're there to feed some of the population. They're there to protect the soil. And we would like to have carbon input 100% of the time. Now when you go in the nutrient cycling, we take that crop biomass that's 46% carbon. It becomes organic matter at 58% carbon. There's a difference of 12%. That 12% in mass is all these other nutrients that are coming available to the next plant. And so we have to understand that these are important, and these are a big factor in allowing David to reduce the amount of fertilizer he's applying to the crops. So I ask you, which is better, pulling iron or pushing carbon? I hope I can get you to think about pushing carbon. And in case you can't see that arrow there, There's David out hiding in his cover crop. So, food security, from my perspective, depends on bringing together no tillage, minimizing the carbon loss, and cover crop mixes, maximizing the carbon input because of all the environmental benefits. Carbon sequestration is important to us in agriculture, and I like to think of that as a wagon wheel. The wheel is a sign of progress, a symbol of strength, a symbol of unity. The hub of that wheel is carbon, and each one of those spokes going through there is an individual environmental benefit that we can point out and quantify. And so each one of those benefits by themselves is no big deal, but when you put them all together in an integrated package, they become a very big deal for the government, for the environment. And I think carbon management is agriculture's wheel of fortune. So soil health is the new genre for conservation agriculture. I've got this list of all the benefits, and I don't have time to talk to you about them, but I want you to understand there's many, many benefits that we're now just starting to identify associated with this unique combination of no-tillage and cover crop mixes. Diversity is a big part of it, and I'll be happy to answer questions afterwards. So, from my perspective, if we want to stop some erosion, save a little carbon, it's time to pack away the plows. When we start considering the biological implications, it's got a whole other story because we've got to protect the little workers in that factory that are doing this work for us. So, we have to worry about plant protection and soil protection for the food security that's important to me. To me, this involves carbon management above the soil surface and below the soil surface, as Ray talked about this morning. So food security, I think, is very important, and I'm convinced it depends on carbon management. So now, one of the things I take 30 seconds to do is get you to understand what a pioneer no-till farmer is doing for you in terms of maintaining your food security. I think we are making gradual transitions to getting more and more no-till and cover crops. And our no-till pioneers are doing this in small doses. The no-till pioneers, they have a unique vision of doing something better. They're passionate. They're sharing and caring. David's taken 3 or 4 days just to put this on, and that doesn't include the 10 days, 20 days of planning that he's been doing over the last 2 months. You never see that in many other industries where they're willing to share, take the time to help you understand better what they're doing. They have a level of ingenuity that boggles my mind and creativity. And you see that in some of these combinations, and that cedar that's out there is part of that creativity. They are risk takers, and they have the courage to travel down the road in untrodden paths, and they have ethical standards. So, I think they're making the world a better place for the rest of us, and we need, and they need our support and gratitude. And for all the other no-till pioneers in here, Ray, Gail, and the other ones, and I don't want to name them, I think we owe them a round of applause because they are the ones that's going to provide us food security 5 and 10 generations down the road. Their actions now will have big payoffs later, and right now we don't really appreciate it. But I think that's going to be the foundation. And so I'd like you to join me in a round of applause for David sponsoring this and the other no-till farmers. So I end with my cartoon character, Carby Carbon.
Thank you, Don. Thank you very much.